So to wrap up this particular case study, we're going to take a step back and evaluate the pros and cons of everything we've just seen. And I will try my best to always give you the pros and cons of everything. So as I'm fond of saying, it's not all unicorns and rainbows. There's good things that come with any abstraction, with any framework, with any technology, and there's other things that could be done better. And that, of course, motivates further enhancements and advances and innovations in our field because people want to do something better than what they were given before. But since we're glass half full people, at least for the next couple minutes, let's start discussing the pros of this particular implementation. So one of the great things about this particular implementation is just how absolutely trivial it was to go from the sequential version of this stuff to the parallel version. Really, all we had to do was take the sequential version. This is what the sequential version looks like. I didn't even bother covering it because it's so similar. And we go ahead and have the parallel version. And as you can see, the only difference is we go from stream to parallel stream. So what's not to like? If you think about it, one of the great things about this particular programming abstraction here is that once you get your head around the learning curve of writing functional code with streams, you can make it parallel with very little effort. Now, as to earlier discussions we had in another lesson, it may or may not be the best thing to do to make it a parallel stream, but if it turns out it doesn't make any difference, it's trivial to back it out and go back to sequential stream with very little work. Moreover, as you can see, when we ran this on a multi-core processor, even one that was as meager as the one I had a couple years ago, which only had a quad-core, hyperthreaded Intel processor, 2.7 gigahertz processor with 32 gigs of RAM, we still get this pretty much, super linear speed up here in performance by just making that one absolutely tiny trivial change. Now, it's interesting to note that there's other ways of doing this, and as we like to say, your mileage may vary. So if we were to run this on a different environment, so this was another computer I used to have, which was a quad-core MacBook Pro, which had 16 gigs of RAM, a little bit faster processor. You can see that the performance, it was actually faster here because the absolute time was better because it was a faster processor. And you can also see, once again, that the sequential stream version was about 1600 milliseconds, and the parallel streams version was about 375 milliseconds. So again, you're seeing this superlinear speedup. Why are we seeing superlinear speedups? That's because these processors have so-called hyperthreaded or virtual cores, and you can read more about them. But basically, this is the way that a hyperthreaded core works. It increases the number of independent instructions in the pipeline using what's called a superscalar architecture. And it allows you to be able to execute more than one instruction during a clock cycle by simultaneously dispatching multiple instructions to different execution units. So it's basically, under the right circumstances, it's a way of having things run faster without having to go to the trouble of having more cores, more physical cores. So you have virtual cores. Now, this doesn't always work out, and you have to have special compilers and other things that know how to do these kinds of layouts. So it's not as good as having physical cores, but it'll make things a little faster, and as we can see, it makes it ever so slightly faster. Yes, sir? So the question is, wouldn't a, quote, normal architecture also execute multiple instructions? Well, if it's got superscalar capabilities, yes. But normal architecture, I mean, if a normal architecture is defined as a non-superscalar architecture, it would not. But it's becoming increasingly popular and common to do this. By the way, a question arises, why do we have so many cores? Why do we have superscalar operations in processors? And the basic reason is that we're continuing to be able to pack more and more transistors on a chip. So Moore's law continues from the point of view of roughly doubling the number of transistors on a chip every 18 to 24 months. It's just that we haven't been able to get those the clock speed to run any faster or run much faster. So we're kind of clocked out, if you will, on maybe close to 4 gigahertz processors at this point. That probably is kind of pushing it. Depends on how they optimize and overdrive and stuff like that. But that's kind of where it's kind of petered out. But we can still have lots of transistors, so they take advantage of all those transistors by having more cores. As I mentioned before, there are some downsides with using parallel streams, and there's some downsides with this. And the main downside is just because it was absolutely trivial to make these tiny, minuscule changes in order to be able to make sequential code run in parallel doesn't necessarily mean that's the best way to do things. Now, having said that, most of the time in real life, you'd be very happy with a super linear speed up with no extra work or almost minuscule extra work. That's like you declare victory, take the rest of the day off, go home, drink a protein shake or whatever you're going to do, and you'd be very satisfied. But if you really want to push things to the limit, there are other ways of running things that are even more efficient. And of course, your mileage may vary, so that's why you always have to be thorough and benchmark your code. And there's a bunch of techniques you could use, like the Java micro-harness benchmarking framework, micro-benchmarking harness, JMH, which is a way of kind of controlling for certain things that otherwise make your code non-deterministic when it runs. But in the interests of completeness and full disclosure, later, probably next class, we will talk about something called the parallel splitterator implementation. And this goes one step further than the parallel streams, so it'll actually run even more things in parallel. So it'll search each string. Each string will be searched in parallel. Each phrase within a string will be searched in parallel. And then within a search for a phrase within a string, that will be searched in parallel as well. So we're going to have very aggressive, a three-headed monster like, Cherubus or whatever, the dog that guards the gate to Hades in Greek mythology. And so it'll be really cool. It's more complicated, of course, but it will give you the sort of the maximal speed up, which is very neat. And again, the key point to note from this is if you put a little bit extra work into your code by using these frameworks, you can maximally extract pretty much all the parallelism you can on the platform, which is really cool. Okay, so that's the end of our discussion of Java parallel streams, the first case study we're going to look at. We're going to look at a couple more case studies later. Why does all this matter? Because your assignment 1B programming assignment will have you using parallel streams to get the speed up we talked about, and you'll get a chance to understand very viscerally how you can take sequential stream implementation and with just a few microscopic minuscule changes make it run a lot faster. So that'll help refine that in more detail.